So last week you guys did the weight versus mass lab, and hopefully you remember that weight is just the force of gravity acting on an object. And we call that F sub g, and that mass is the amount of substance, or the amount of stuff, or kind of more importantly for this class, the amount of inertia. It's a measure of the inertia of an object. And our symbol for that is little m. And so we talked about things like you use a scale to measure weight. Oops, my fault. And that scale's got a spring inside of it that bends a little bit, and then you calibrate that thing in units called newtons. And for mass, you use balance, and the SI unit of mass is the kilogram. So we did a little experiment. You just took a whole bunch of known masses and you hung them on a scale, and then you tried to find the relationship between the weight and the mass. So you made a graph, weight versus mass, and at this point it's about, 8:20 on Wednesday night, and it looks like about 2/3 of you have filled out that little form, and most of you guys said, hey, my graph looks like this. And then a lot of you guys said, oh, this is a linear relationship, but actually it is a linear relationship, but it's a special kind of linear relationship. Remember, please, that when we have a linear relationship with a zero y-intercept, we know that what we're looking at is a directly proportional relationship. So the force of gravity, the weight, is directly proportional to the mass. And right there is pretty much why everybody uses weight and mass interchangeably, is that all you really want to know is how much do you have. And so if one of them doubles and the other one doubles, then it's a pretty good number for how much do you have, whether you're talking about pounds or newtons or kilograms. It's kind of like when you say, how far away from school do you live? Oh, I live 5 minutes. Okay, 5 minutes is kind of a weird thing to talk about, because 5 minutes is a weird unit, because when you talk about how far, you're usually thinking about distance, but you give them an answer that's measured in time. So let's look at this weight versus mass. If the weight is directly proportional to the mass, that means that the force of gravity is equal to something times the mass, and that something is our constant of proportionality, or our slope of the graph. And it's kind of cool looking at your post-lab forms, because it looks like most of you guys did some careful measuring, and the accepted value for that slope is actually 9.81 newtons per kilogram. And what does that slope tell us? It tells us that every kilogram of mass weighs 9.81 newtons. It's the rate of change in the weight with respect to the mass of the object. The last question on that little survey was, what do you have to do in order to get a different slope for this experiment? And some of you guys came up with like some kind of clever out-of-the-box answers, like, oh, let's just use something that's calibrated in pounds. And that would actually give you a different slope, but when you change the units back to newtons per kilogram, you'd still get the same slope. Most of you guys, of course, know that what you have to do is actually go to a different planet, and that's why we didn't do the experiment twice and get two different slopes. It's because we'd have to go someplace else to get a different slope. So this slope has something to do with where we are. And where we are is on the Earth, or more specifically, in the Earth's gravitational field. And just in case you don't remember, we talked about this a little bit, a gravitational field is simply an area where an object experiences a gravitational force. So this number here, 9.81 newtons per kilogram, tells us something about the gravitational field. And what it is, it's the gravitational field strength. So 9.81 newtons per kilogram is the gravitational field strength, the strength of the gravitational field. And that gets the variable little g. Okay, so the strength of the gravitational field on the Earth is 9.81 newtons for every kilogram. You guys, if you did the reading, probably saw something about 1 kilogram weighs 2.2 pounds on the Earth. So that would be your different units, right? So if the gravitational field strength on Earth is 9.81 newtons per kilogram, then it is 2.2 pounds per kilogram. Okay. So keep in mind, this is not a conversion factor like when you say 2.54 centimeters equals 1 inch, because 2.54 centimeters and 1 inch are both measuring the same kind of physical quantity, the same unit of length. But 9.81 newtons per kilogram is actually a rate. It's the strength of the gravitational field. It's measuring a different physical quantity. So that gives us a general, if the force of gravity equals 9.81 newtons per kilogram times m, then the weight equals little g times m. But most people don't write it in that order. Most people write m times g. Just, I don't know, feels better that way. So weight equals mass times the gravitational field strength. An important thing here is usually when we write force of gravity, we think of it as a vector quantity, and it is. Another way you could write this equation is that the force of gravity, the vector, is equal to the mass times gravitational field strength, the vector. So if you're the Earth, right, and I'm standing, I don't know, here. Hello, I'm standing here. You would feel a force of gravity this way, right? You would also feel, because you are in a gravitational field that points this way. Gravitational field is a vector quantity as well. Okay, so you guys can probably imagine what the gravitational field looks like around the Earth, right? It kind of points toward the middle. And like we were talking about how you have to change where you are to change the gravitational field strength, if we get farther and farther away from the Earth, g gets smaller. The strength of the gravitational field decreases. All right, so this is our general equation that we get from the lab. Fg equals mg. I don't tell you to memorize a whole lot of stuff, but this is an equation you're probably going to use, I don't know, every single day in this class, so you will get to know it. Another weird thing is sometimes people just shorten this to 10 newtons per kilogram if they're not really worried about sig figs, if they're not worried about the precision of their measurements, and they just kind of want a rough answer.